So now we're going to look at how we can compute the mean, variance, and standard deviation for a binomial random variable, where the mean, mu, is just given by n times p. And it's a pretty understandable value if you get the idea of what a binomial distribution looks like, that if you want to find out how many successes you expect to get, you should just multiply the number of trials times the probability of a success. Pretty straightforward in that way. That if you flip a coin 10 times, you would expect to get 5 heads or 5 tails. It's really, in my opinion, the nicest mean formula to get. And the formulas for variance and standard deviation are also pretty far onto the nice side here, but they're not quite as intuitively sensible, I would say. That for variance, we take NPQ, where, in my opinion, a nice way to think about what's going on here is that as we take more trials, you would expect there to be more room for change. There'd be more possibility that that value PQ gets bigger and bigger. So you'd expect there to be more spread for the data. And then also, in terms of these values P and Q, the number here gets as big as it can possibly get when those are the same. That's when you have the most possible variation is when you're just as likely to get a success as you are a failure. And then standard deviations, what standard deviation always is, it's the square root of variance. So just take the square root of NPQ. And to see this, we're going to take one more example. So here we say that in Fort Myers, Florida, it rains on about 51.3% of days in September, where we want to find the mean, variance, and standard deviation for the number of days it rains in the month of September. Where for this, it's just a matter of using the formulas. Here, we have n is equal to 30, because there are 30 days in September. P is equal to 0.513, because we say there is a 51.3% chance of rain in September. And as a result, Q would have to be 0.487. So, with these three values in tow, it's pretty quick to get our mean, variance, and standard deviation. That mu here would end up being 30 times 0.513, or approximately 15.4, while the variance sigma is going to be 30 times 0.513 times 0.487, so you can think of that as actually just the mean times the value for Q, which here will end up being about 7.5, and then finally, oh, that should be sigma squared, excuse me, getting to sigma by itself. Well, we just take this chain of information in there, 30 times 0.513 times 0.487, and throw it all underneath a radical to get a value of approximately 2.7. And this is essentially all we need for this section, for this unit. But before we get done with this, I do want to take a brief moment here to discuss something important that we haven't really seen anything from yet, at least not explicitly, but that we're going to be seeing a lot of in Chapter 5, and that our work in the calculator in this section hinted at with things called probability mass, probability density, cumulative mass, cumulative density, basically what are called our distribution functions. And that's what we'll finish with.